Hello, and welcome to the third and final video of this series, where in this video I'll be demonstrating that the fanning frictional factor for laminar flow is always equal to 16 over Reynolds number. So in this problem, I've gone ahead and written three different equations. The first one being what we're solving for. We're demonstrating that the fanning frictional factor is equal to 16 over Reynolds number for all of the laminar flow in these situations. Then under I have Reynolds number, which we've discussed many times before, which is simply rho dV over mu. And then I have the generic equation that is used countless of times for the heating coefficient that we'll be plugging back into our equation to solve for the fanning frictional coefficient. So first off, explain this problem a little bit. I'm going to draw a little bit of a diagram here of our two cylinders, where inside we have an unfilled fluid going up, right? And then at each of these end caps we have a different pressure. This one we have is called P1, and at this end we have another one, P2. And then I'm going to call this distance of the outer cylinder, max distance, as dz, delta zeta. Right? Okay, so now we understand a little bit more what we're doing. What we're going to be doing now is we'll be deriving a force balance equation, and then from there we'll be getting the deriving an expression for the flow rate, and then from there we'll get expression for the volumetric flow rate, and then in turn plug back in Reynolds number and Bernoulli's equation to get back to our fanning frictional factor. So like I said, we're going to start off by a force diagram, or force equation. So first off, we'll focus about the two end caps. We know that there's pressure. Let's call it net pressure changing P, whatever. I'm just going to call it P1 minus P2, as we have expressed what both of these are. Multiplied by the area, which this is the circumference of circle, so pi r squared. And then this minus something else is equal to 0. And let's just forget that there is some shear rate for this liquid, and so, or this fluid, and so we're going to be expressing that through tau and multiplied by the area of the whole cylinder. So this is tau multiplied by 2 pi dz r, right? And this is simply equal to 0. Right. What we can do is we can go express our equation for tau, as we know that tau is simply the viscosity times the change volume with respect to radius. Right, mu dv dr. So we go ahead and put that in. Do it on the other side so that we get mu dv over dr times 2 pi dz(r) is equal to what we have on the first part, P1 minus P2 times pi r squared. So we go ahead and express this from left side to right side, just divide this by this. So we get dv dr is equal to P1 minus P2 times pi r squared divided by 2 pi mu 2 pi. Alright, I'm just gonna break this a little bit. We have 2 pi, take this out, and then r, so this times r, this becomes 2 dz mu, right? dv dx. Alright, and from here we can go and derive this right hand side, so we get for flow rate. So we get P1 minus P2 R 2 dz mu plus C. Or sorry, I don't know why I just did that. We did R, so this becomes R squared over 2 plus C. V becomes P1 minus P2 all over 4 dz mu times r squared plus c. sorry, I don't know what happened here. This should be added together. So if we add this, we subtract from the left side, this becomes negative. This is all negative. Okay. Should be good. And then, so what we can do is we can plug in a value for R. We know that when R is equal to big R and is on the outer cylinder, we know that the velocity is 0, right? Because what we said before, something touching the outside of the liquid is equal to the velocity of that solid. So then we go ahead and plug this in. Yeah. So that we can go ahead and combine this so that we get our constant C. The equation is equal to, take this out, so we get P1 minus P2 all over 4 mu dz times R squared minus R squared. Alright, that's our expression, and then if we know that, to note that the momentum per velocity is equal to the average velocity multiplied by the area, right? So what we can do is multiply this expression by the area so that we get the volumetric flow rate, right? So go ahead and plug this over here. We said we have this multiplied by the area, so we're going to have the integral of P1 minus P2 over 4 mu dz multiplied by R squared minus R squared. And then what I said, we're multiplying by the area, so that this becomes 2 pi r dr, right? Then we can go ahead, multiply this out and get the constants and work this out for our momentum, right? So we get constants, we get P1 minus P2 multiplied by 2, this becomes 2, we have pi, this becomes pi out here, radius cancels out here, so this becomes the same, dz, and then we multiply it by this, so we go from 0 to big R, this multiplied by just the little r, so this becomes big R squared little r minus little r cubed, right? And then if we go ahead and rewrite, I'm just going to rewrite the second part, this derivation, so that this becomes big R squared little r squared over 2 minus little r squared, or little r to the 4th over 4, right? R to the 4, yeah? And then this is going to be still from big R to 0. We simply just plug in big R for little r, so that we end up getting R to the 4th over 2 minus R to the 4th over 4. Multiply this first one, we get 2R to the 4th over 4 minus R to the 4th over 4, which is simply R to the 4th over 4. Go ahead and plug this back into here. So we get Q is equal to P1 minus P2 pi. We have 2 mu dz, then multiplied by, we said, R to the 4th over 4. So then this becomes P1 minus P2 times pi all over 8 mu dz times R to the 4th. Alright, then what we can do here to start simplifying even more, we can plug in the diameter for the radius, right? We know that radius is equal to diameter over 2, so that this becomes diameter 4th to 2 to the power of 4, right? So we get Q Q is equal to P1 minus P2 times, I'm just going to write this here, so we have d to the fourth pi over 2 to the fourth times 2 to the fourth, this becomes 128, right? Mu dz. Alright, there's our expression for our volumetric flow rate. I'm going to go ahead, free up some space here so we can go ahead and rework this equation to get our answer. Should be good. Okay, what I'm going to do here now is rewrite this equation for the change in pressure, right? Might not make any sense right now, but we'll be using Bernoulli's equation to be solving for that and then plugging them into each other. So if I rewrite this, I get P1 minus P2. Yep. So this multiplied by that, so this becomes 128 Q mu dz divided by pi d to the fourth. That's our expression. Then now what I said, we were going to be using Bernoulli's equation. Since we know that in here there is no change in altitude, no change in the different velocities, so we know that the only thing is changing is the pressure, right, from the two end caps. So what we can do for Bernoulli's equation, we can simply write it as net change, so P2 minus P1 over rho density, simply equal to the negative heating coefficient for this expression, right? So as you can see, we have the inverse here, P2 minus 1, P1 minus 2. So what I'm going to do is get the negative inverse of this whole expression, so that we get P1 minus P2 over rho is equal to that. Alright, so I'm going to go ahead and plug this expression into here for P1 over P2, so that we get heating coefficient is equal to 128 Q mu dz over pi d4, so pi rho d to the fourth. Alright, then as we can say, I wrote this equation back up earlier. I will be using it later. This is where it comes in. We simply equal this to that expression as they are the same thing. So that I get 2 times dz times d velocity squared. Right, then I'm going to go ahead and rewrite this just with these two expressions. So we're going to move up, take this 2, this becomes 64, Q remains here, we have a mu remains, dz divided by dz, so that goes away. I'll write this on this side so I know I'm keeping. Then this side, so then pi remains here, rho also remains, and d to the fourth multiplied by d, so this becomes d cubed. Okay. Then v squared, v to the negative 2. We have everything. Yes, we do. And now the final step is to rewrite this expression for the volumetric flow rate. As we said earlier, volumetric flow rate is simply equal to the average velocity multiplied by the area. So what I'm going to do here is just plug it into here. For Q is equal to the velocity times pi. Instead of writing the radius, since there are no radius, we're talking about diameter, and then also Reynolds number talks about diameter. R squared becomes d squared to the 2, so this becomes d squared to the fourth. Plug that equation in for Q, so that we get F is equal to 64 V pi d squared mu all over pi rho d cubed v squared 4. Now we simply rewrite this for like terms. 64 over 4, that becomes 16, right? V over v squared, that becomes v. Pi over pi, that goes away. D squared, and then d cubed. We have a d in the denominator, and we have a mu that remains on the top. And then left over, we have rho. As you can see, our fanning friction coefficient. Next one really quick. Is equal to 16 mu over rho dV. As you can say, we said this Reynolds equation that we brought up at the beginning, which is rho dV over mu. If we do the inverse of that, we get mu over rho dV. As you can notice, that is exactly what we have here, right? So if we plug in rho over dV, that's 1 over RE, 1 over Reynolds number. So that finally, we get that the fractional frictional force is equal to 16 all over Reynolds number for this situation in all laminar flow. So hopefully this video helped you guys out, and hope you have a good rest of your afternoon.